the sea and its unique inhabitants. Many miracles happen in unexpected locations. The North Sea and the Baltic, as we have never seen them before.
Think of protected forests, isolated islands, and reserves where nature should be safest. Yet, invasions repeatedly take root. That same pattern reached cold northern waters, where thousands of eels were deliberately released to confront a spreading ecological threat. This story begins beneath the surface, where an unseen plague travels farther than any animal could.
I'm going to tell you almost everything you need to know about the signal crayfish.
So let us start with facts. The invasion beneath the surface. Across northern Europe, rivers and lakes once defined by balance now carry an unfamiliar pressure, one that arrived quietly and spread without resistance. In Estonia, Sweden, and Finland, fishermen began noticing empty traps, collapsing banks, and native crayfish vanishing from waters that had supported them for centuries. The culprit was not pollution or overfishing alone, but a newcomer with a hard shell and an aggressive appetite, the North American signal crayfish. Introduced deliberately and accidentally throughout the 20th century, this species expanded with alarming speed, outcompeting local wildlife and reshaping riverbeds from below. Unlike native crayfish, it reproduced rapidly, tolerated poor water quality, and occupied every crevice it could reach, leaving little space for anything else. What made the invasion especially devastating was its invisibility, because by the time populations were noticed, ecosystems were already unraveling. Scientists soon realized the problem extended beyond Estonia's borders, forming a creeping network of infestations around the Baltic Sea. Each new report sounded familiar. Another lake transformed, another native population pushed toward collapse. Yet beneath this visible takeover, an even more destructive force was moving, one that would redefine the crisis entirely. At first, authorities underestimated how quickly this quiet transformation could spread unchecked. The unseen plague. At first glance, the signal crayfish looked like just another invasive species, aggressive, fast-breeding, and ecologically disruptive. But hidden inside many of them was something far more lethal than sharp claws or territorial behavior. These crustaceans carried a fungal pathogen known as Aphanomyces astaci, the crayfish plague. To native European species, it is nearly always fatal, and the irony is brutal. The invaders carry it without harm, spreading death to their cousins with every step. The crayfish plague is not new. It was first documented in the 1860s when populations of European crayfish began mysteriously dying off in droves. By the mid-20th century, the disease had wiped out native populations across large parts of the continent. Desperate to restore commercial and recreational crayfishing, officials introduced the hardy North American signal crayfish into European waters. It was assumed to be a solution, but the species turned out to be the plague's primary carrier. The fungus destroys native crayfish from the inside, infiltrating soft tissue and causing complete mortality in most outbreaks. Waterways once teeming with life now face a near total collapse of benthic diversity. Plants uprooted, fish eggs consumed, food chains disrupted. Unlike more visible environmental disasters, this one spreads in silence, unnoticed until it's too late. But even that wasn't the most terrifying part. Researchers soon discovered the plague didn't even need a living carrier. Its spores could survive in damp conditions, on nets, boats, or even the soles of waders, for up to 2 weeks. A single careless visit to a lake, a wet boot left unwashed, could unknowingly carry the infection into a new body of water. In the end, it wasn't just the crayfish spreading the plague, it was the people chasing them. The boots that carried death. The realization hit harder than any ecological model could predict. The most efficient courier of this underwater plague wasn't a creature, it was us. Not through malice, but through routine. Every fishing trip, research outing, or canoeing excursion became a potential act of biological sabotage. A damp boot, a borrowed bucket, or even a net dried too late could harbor spores of Aphanomyces astaci, the crayfish plague, long after contact with infected waters. And while the pathogen remains invisible, its consequences are anything but. In controlled experiments, researchers discovered that, under moist conditions, the plague spores can remain viable for up to 14 days, an eternity in microbial terms. That means a fisherman could unknowingly transport a microscopic killer from a contaminated stream to a pristine lake over a weekend. And unlike the invasive crayfish, which at least can be seen, heard, and measured, the spores carry no scent, no trail, and no warning until native populations begin to die en masse. This startling insight reshaped the conservation strategy. Scientists began not only mapping crayfish infestations, but also tracking human access points, parking lots near riverbanks, trailheads used by anglers, and popular wading sites. Each one became a potential outbreak origin. Suddenly, the front line wasn't just under the water. It was in the trunks of cars, in rental gear, in forgotten plastic crates stacked at the back of sheds. Educational campaigns were launched to raise awareness among local communities, urging them to disinfect gear and avoid cross-contamination. But despite increased outreach, enforcement remains nearly impossible. In many rural areas, where lakes and rivers connect like veins, a single unwashed kayak can undo months of careful containment work. So, when traditional tools failed, traps too slow, poison too dangerous, electricity too weak, biologists began to ask, what if the answer wasn't in stopping the plague from entering, but in finding something that could stop it from thriving once it did? The predator returns. Long before the signal crayfish arrived, before the plague drifted downstream, the rivers of northern Europe had a native guardian, the European eel, elusive and ancient, once moved freely, gliding through beds, weaving into crevices, hunting under the cover of darkness. Over centuries, its numbers dwindled due to habitat loss and overfishing. Now, it was being summoned back, not just to survive, but to hunt. Scientists at the Estonian University of Life Sciences turned to this native species for an unconventional method of biological control. Eels are bottom feeders, nocturnal like crayfish, and equipped with a keen sense of smell. Their shape allows them to reach the rocky hideouts that protect invasive species. Most importantly, they belong here, unlike past introductions that went wrong. To test the idea, researchers set up 6 water tanks with filters, netting, and underwater cameras. 21 narrow-headed and 21 broad-headed eels were introduced, allowed to acclimate, then fed live invasive crayfish. Every movement was recorded. The results were promising. Eels hunted the crayfish and seemed to prefer them. Broad-headed eels with larger jaws proved more effective, consuming over 80% of crayfish in some trials. The juveniles, too small for traps, were easy targets. It wasn't a massacre, it was a method. This wasn't just about numbers, it was a story of balance, a native predator, once nearly erased, returning as a counterforce. But nature is never simple, and soon, the eels themselves would show how survival reshapes the hunter. The shape of a hunter. At first glance, one eel looks much like another, long, slippery, and silent. But as researchers studied the feeding trials more closely, they noticed something curious. Some eels struck harder, faster, and with greater accuracy. Their heads were wider, their jaws more muscular. These were the broad-headed eels, and they were better suited for the task. Not because of chance, but because of how they had lived. It turns out that an eel's head isn't fixed by genetics alone. It's shaped by diet. In environments where food is soft, like pellets or larvae, eels tend to develop narrower heads, optimized for suction feeding. But when their prey is tougher, harder to crack, the eels adapt. Their skulls grow broader, their bite force increases, and their behavior changes. Evolution, compressed into the span of a few formative years. This distinction had real consequences. In the Estonian experiments, broad-headed eels devoured up to 83% of the crayfish they encountered. Narrow-headed ones, only 33%. The difference wasn't just in appetite, it was in armor-piercing capacity. This revelation forced researchers to rethink eel reintroduction, not just as a conservation effort, but as a form of ecological engineering. If the goal was to build better predators, they would need to begin not in the wild, but in hatcheries, feeding juvenile eels hard food from the start to sculpt their skulls into weapons. But with power comes risk. Would these enhanced eels turn on the last fragile populations of native crayfish clinging to survival? That question led to yet another experiment and a stroke of luck. It turns out that eels show a strong preference for smaller prey, especially those under 7 centimeters, which conveniently matches the size of invasive juveniles too small for traps. The native crayfish, fewer and often larger, were largely ignored. It wasn't a perfect solution, but it was, for the first time, a hopeful one. The battlefields and barriers. Armed with data, instincts, and centuries of coevolution, the eels were ready. In early 2024, biologists released 1,200 of them, farm-raised, disease-checked, and broad-headed, into 2 Estonian water bodies, the Rapka Reservoir and the Rumu Quarry. These quiet, unassuming places would become living laboratories, where scientists hope to watch nature fight back against one of its most devastating invaders. But Estonia wasn't alone. Similar strategies were unfolding elsewhere. In Scotland's Loch Ken, more than 700,000 signal crayfish had already been trapped in just 5 months, a staggering number that barely dented the population. Desperate for solutions, conservationists began reinforcing native predator populations, hoping to tip the balance through biology rather than brute force. Still, predators alone couldn't stem the tide. In Switzerland, the approach turned architectural. Between 2013 and 2016, scientists constructed 8 experimental barriers in streams, designed not to block fish, but to stop crayfish. Some worked. Others were outwitted by what one researcher described as ninja crayfish, crawling over damp rocks, slipping past during slow currents, or even scaling algae-covered walls. Despite their limitations, barriers offered a passive defense, one that didn't rely on constant trapping or poisoning. But they came at a cost. Each new wall threatened to fragment aquatic habitats, impeding native species like the already imperiled eel. The choice became philosophical as much as ecological: protect the present or preserve the future. The answer, as researchers were learning, would likely require both. They nearly lost entire ecosystems to something that hitched a ride on a damp boot. But nature doesn't just surrender, it adapts, it strikes back, sometimes with teeth. If this story stirred something, drop a thought below, subscribe for more, and we'll dive deeper next time.